Hi, I'm going to show you how to make your own blockchain in under 3 minutes using the Babel DSL, which is the programming language that allows you to create blockchains. It's kind of like an add-on to the Scala programming language. And the way that this works is you create first a like state machine essentially out of this thing called cocell. So this represents a transformation between your starting data type, like in a traditional blockchain, like a transaction, and the output type being like a block, right? You import this class, you create an instance of it, and within this class, you have to define something called a cell. And so a cell is a monad that carries the different steps inside of your consensus process. It's like a consensus state machine, basically, that's typed. So here I have the implementation of a layer one blockchain. Um, for us, we call it a state channel. And this is built using FS2 strings. And this right here is an algebra, like sorry, coalgebra, which is a build-up method for creating a functor or a monad, the same monad called a cell that we talked about. And these are the different steps that, when we receive a message from a node, we put them, we basically use the message for the various different step in the consensus process. And we create a functor to then do the state transformation from the beginning to end. So here's a coalgebra for one. Here's another, the algebra, which tears down the functor. And by passing those in, you create a consensus process using the cell. And each one of these different case statements here is basically the step in your consensus monad. So what's really cool too is that we have this concept called a composition operator, which allows us to take multiple different consensus processes and sort of compose them with one another. So here I have the layer zero process, which connects any L1 blockchain to all other L1 blockchains using reality's L0. This is already a pre-baked implementation that you can just import from the library. And I also have like a basic L2 process, something that sits. It is, like as a separate process, not actually running consensus, just outside of the L1, which is going to spam transactions. Um, or process transactions. Either way, it's like spam it if it's in a cluster or like, just process like based upon what I'm doing right now. So I have this really simple example. And basically, I'm going to send this information into an L2, which is then going to kick off the pipeline between to send from its internal process through the L1 to the L0. And what this does is it takes that pipeline and composition operator, creates an instance of it, and just passes the data right through it. So this is, fully invoked and then used. And if you want to actually build a cluster out of this, all you have to do is use our like Docker setup here to just like launch a local cluster, or you can just take the individual fat jars and put them on any kind of device you want, cell phones, laptops, AWS instances, and connect things together. So that was really simple, but there's a lot more stuff I can show you, like how to create different types of streaming topologies, how to basically like lift information into these different consensus processes as well, and then also how to host Turing complete code that implicitly has a ZK proof generated, so you can prove that things hosted on all these different devices actually did what you thought they were. Um, that is what I'm going to talk about in the next few ones, but all of the links to this code and how to get started and the documentation are online right now. So you guys should get involved. And this is very, very cool. Yeah, imagine if you're smart, if smart contracts could like implement blockchains, like if you could literally use Solidity to build your own blockchain. Well, that's what this does. And it has the same, like, it's the same type of like a theorem prover as Agda and Cock, those theorem provers out there, so you can like have certain guarantees of compile time that your code's actually going to complete. It is a domain-specific language for fault-free computation, and yeah, sort of like an add-on to the Scala programming language. You're welcome.